Science in pajamas. All right, so today we're going to talk about forces and vectors. Just like acceleration, motion, velocity, forces aren't always going to be side to side or up and down. It can be both. It can be at a diagonal, and then we have to um, or we have to figure out what the net force would be and in what direction. But the nice thing about this is we know exactly how to do this already. We've done it with acceleration, velocity, all that stuff. It's the same method, just using different symbols. Like for force, we're going to use F for force instead of V for velocity. So we already know exactly how to do this. We're not going to teach you anything new. We're just going to teach you how to apply previous ideas to forces now. Before we do, though, I want to talk about equilibrium. Equilibrium is when all of the forces balance out, so there's no net force. So maybe we have a car that's moving. I don't want to use that marker. That one does not do well on this board. All right. So we have a car. All right. And let's say it's experiencing 800 newtons as its force of gravity. It's experiencing 800 newtons as its normal force. It's experiencing 200 newtons as its applied force, and the frictional force equals 200 newtons. Now before, when we talked about similar ideas like with motion and all that, we said that if things are going in opposite directions, then we make one of them positive and one of them negative. Typically we use up and to the right as positive and down and to the left as negative. So we can, and just like before, we want to combine the forces in the same plane. So here we have our horizontal plane, our x-plane. So we're going to take, this one's going to be positive because it's going to the right. This one's going to be negative because it's going to the left. So force in the x direction would be positive 200 newtons for the applied force plus negative 200 newtons for the frictional force. And we end up with the force in the x direction is 0 newtons. All right, well, let's look in the y direction. Again, this one's going up, so we're going to say that one's positive. This one's going down, so we're going to say that one's negative. So force in the y direction equals positive 800 newtons plus negative 800 newtons, and we get 0 newtons. So overall, there's no net force acting on this car, which means it's moving at a constant velocity. And even though there are forces going in 4 different directions, up, down, left, right, they all still balance out to 0. So that's what we mean when we say an object is in equilibrium. But what is not in equilibrium, huh? What if instead of being in equilibrium, it is, well, it has a net force? How do we figure that out? How do we figure out the direction? Just like we've done before. So here's our first problem. We're going to start off easy and then move up to some of the ones with harder calculations. So a car is accelerating downhill under a net force of 3,674 newtons. What additional force would cause the car to have constant velocity? In other words, to be in equilibrium. So we have our car. It's going downhill. And it has a force going down the hill that is 3,674 newtons. What do we need to balance that out? What do we need to no longer be accelerating, but to be going at a constant velocity? So what do we need to balance out? Well, if we think about equilibrium, that means that we want an equal force in the opposite direction. Newton's third law. So if this is 3,674 newtons, that means that the way we would want it to be is negative 3,674 newtons, or you can say 3,674 newtons in the opposite direction. So that means that it would be 3,674 newtons in that direction. Yeah, not too bad. That's the easy one. Let's do some harder ones. Yeah. Alrighty. Got that down. Alright, so. There it is. We have a sailboat problem. Forces acting on a sailboat are the wind, which is 398 newtons north, and the current, which is 162 newtons. 162 newtons east. If the boat has a mass of 310 kilograms, what is the magnitude and direction of the boat's acceleration? So we have a boat. It is experiencing a wind force that is equal to 398 newtons, as well as a current force of 162 newtons. This kind of looks like an X and Y component that we have to figure out the resultant for. So I'm going to redraw this to make it a little bit easier. So we have force of the wind, force of the current. That should be our resultant force right here. The resultant force. And just like we did before, we are going to do exactly what we did with Pythagorean theorem. Because we know that Pythagorean theorem says a squared plus b squared gives us c squared. So then if a squared plus b squared equals c squared, and c is our resultant, so that's going to be fw squared plus fc squared equals fr squared. Fr would equal the square root of fw squared plus fc squared. Alright, so we go ahead, we plug that in. We have square root of 398 newtons squared plus 162 newtons squared. Our resultant force equals, let's see, like I said, or like I told you guys before, I do all the calculations ahead of time. 429.7 newtons. All right, so that is our resultant force. But it didn't ask us for a resultant force. It asked us for the acceleration. However, we cannot find the acceleration until we know the resultant force. We know force equals mass times acceleration. We need to know that net force. The net force is our resultant. So now that we know our net force, we can plug that in to this equation. So first we want to move it around. So we have, or we're solving for A. Acceleration equals our net force over our mass, which equals 429.7 newtons over our mass, which is 310 kilograms. We go through, we solve that. Our acceleration is 1.4 meters per second squared. So now we have our acceleration, but we also want to know the direction. Now the direction is going to be in the direction of the force, of the net force. Now remember how we found direction previously with problems like this? We use theta and inverse tangent. So I know that this is north, I know that this is east. I'm going to. So theta equals inverse tangent of your y over x value. So the y value is our north value, that's 398 over our y value, which is 162 newtons. And we get our theta, which is 6.1 degrees. Now the question is, how do we reference it? Because 6.1 degrees can be in anywhere. So what we're going to say is, because it's looking at this right here, we can say it is north of east. Because we're starting at the eastern line and we're moving up from it. All right, we got one more that I want us to do, and then we'll move on from there. So see, this is exactly what we've done before. We're just using it for force instead of acceleration or velocity. All right, last problem with this one. A jumping dog experiences a gravitational force of 78 newtons, a normal force of 83 newtons, a forward applied force of 103 newtons, and a frictional force of 56 newtons. What is the net force and direction? So, we have our puppers. He's jumping. I know it's a bad picture. It's okay. And we know that there's a gravitational force of 78 newtons, normal force of 83 newtons. We have a forward applied force of 103 newtons and a frictional force of 56 newtons. All right. Now for ones like this, remember, we're going to look at each plane individually. So let's start with the x-plane. Well, this one's heading forward, so that's positive. This one's going in the opposite direction, so we'll make that negative. So we have force in the x direction is positive 103 newtons plus negative 56 newtons. And for that one, we get positive 47 newtons. For F in the y direction, we have up is positive, opposite of that is down, which is negative. So we have positive 83 newtons plus negative 78 newtons, and we get positive 5 newtons. So that means we have taken all four of these and we've broken it down now, or we've condensed it down into two. We have 47 newtons forward and 5 newtons up. All right, well, we can kind of take this and I'm going to connect them instead. So 5, 47. That is our net force right there. We want to solve for that. So I want to make that a little bit bigger so you guys can see it a little bit better. We have 5. So 47 newtons, 5 newtons. This is our net force. That is our resultant. So now we gotta find the net force of our dog and the direction as well. All right, so we're gonna do it just like we did before. Pythagorean theorem rearranged. So the net force would equal the square root of our y and x values. So we have fx squared plus fy squared. So force net equals square root of 47 squared plus 5 squared equals, and that gives us a net force of 47.3 newtons. So now we got our net force. We still have to find the direction. So again, we're going to kind of find, because we want to do y over x, so we can do theta equals invert tangent of our y value over the x. So that equals inverse tangent of 5 over 47. This was the one that was 6.1 degrees. I apologize. I'll talk about that in a moment. I misread before. That's my bad. All right. So this one is where we have inverse tangents equals 6.1 degrees. And how can we describe it? Well, this is the ground and it's going up from the ground. So it's 6.1 degrees above the horizontal. Ta-da! All done. I do want to make a quick correction to myself with the last problem, though. I was looking at the wrong calculation before when I was doing the theta for that one. So with the sailboat, theta equals inverse tangent, we said, of, 398 over 162. 398 over 162. I looked at the wrong part of my sheet, so I just want to make that correction. It is actually 67.9 degrees north of east. I got messy handwriting. My handwriting's all over my sheet. I'm bound to make mistakes at some point, so I apologize for that. But that'll correct that error. And yeah, if you have any questions, hit me up in our Google Classroom or in class or send me an email. Yeah, you guys take care, stay safe, and stay healthy. All right, bye-bye.